In this lecture, I'll talk about the linearization of nonlinear problems. Now we can take a nonlinear system of conservation laws, and when we look at small perturbations around some steady state, express that in terms of a linear hyperbolic equation for how the perturbations behave. So we'll look at the general form in terms of Jacobian matrix, and then a couple of special cases, just a scalar conservation law, Burgers equation, and the 2x2 system of equations that correspond to compressible gas dynamics in a simple case, which allows us to derive the linear acoustics equations. So in general, we'll look at a nonlinear system. So Q might be a vector with m components, f a function that maps Rm to Rm. But let's suppose now that Q of xt, our solution, is approximately equal to some constant state Q0 plus some small perturbations, which we'll write as Q tilde of xt. So we now want to derive the differential equation that Q tilde satisfies. So if we differentiate that, Qt equals the time derivative of Q0 drops out, that's a constant, and we just get that Q tilde sub t, time derivative of Q tilde, is equal to derivative of Qt, which from the original conservation law is minus f of Qx, and that we can differentiate out as the Jacobian matrix f prime of q times qx. Okay? And then this is at this point still nonlinear because f prime of q in general is a function of q still. But if we assume that we're close to some steady state, then we can write f prime of q plus q tilde as being approximately f prime of q0 times the vector q tilde sub x plus higher order terms, and we'll drop those higher order terms. And when we do that, we end up with the linear system of equations, which now has the form of a linear system q tilde t plus a q tilde x equals 0, where a is the Jacobian matrix evaluated at the constant state q0 that we're linearizing about. So in the case of a scalar equation, this resulting linear equation would simply be an advection equation. A would just be a number, and it would just be advection. A would presumably be a real number. In the case of a system, this f prime of q0 is a matrix. For a system of m equations, we end up with an m by m matrix. But let's first look at the scalar case. So an example, classic nonlinear conservation law with a single variable is Burgers equation. And so here I'll call the variable u rather than q because u sort of represents a velocity, and the nonlinearity that we have is a sort of classic quadratic nonlinearity. F of u is 1/2 u squared, the sort of nonlinearity that comes into gas dynamics equations as well. So this is the simplest sort of scalar nonlinear equation. And if we differentiate f of u with respect to u, we just get u, and so the quasi-linear form of this equation is just ut plus ux equals 0. And that looks like an advection equation, except that the speed u that things are advecting with is actually equal to the solution itself. So the speed of propagation depends on the solution value. And where u is larger, it's propagating faster. Where u is smaller, it's propagating slower. So for example, this plot on the bottom, I didn't put any axes on here, but think of this as u is varying around the 0 state and maybe going up to value 1 at the peak here. So the peak of this wave is traveling faster than lower down values where u is smaller. And so as time evolves, you get this sort of behavior. And as we can see, eventually it sort of steepens up and becomes vertical. And at that point, it would not make sense to have sort of a multi-valued solution with the peak continuing to move faster than the states in front of it. And so at that point, we have to insert a shock wave, and we get into the whole theory of nonlinear shock waves. So we're not going to get into that yet, but this is just kind of a picture of what happens when we take this nonlinear scalar equation where the advection velocity u depends on the solution itself. And that comes from the fact that we started with a nonlinear flux function, and differentiating it still gave us a function of u. But if we look at the same equation and now look at a situation where u is varying only a small amount about some constant value. So again, I didn't put x's on here, but suppose now that this is, the value 1, and the peak up here is something like maybe 1 plus some small epsilon. 1 plus some small epsilon. Then again, with this advection equation, the peak is going to travel faster than other values, but it's basically all moving along at speed of approximately 1. And until you get to very large times, you wouldn't really see much deformation of this, not like we saw in the previous picture. And so this would be a case where it would make sense to linearize this equation. And in this case, the flux function is a half u squared. And so the derivative, the Jacobian, f prime is just u. And if we linearize about some state u0, so here, for example, we might take u0 equals 1, the state that we're linearizing about, or any value between 1 and 1 plus epsilon, say, then what we'd end up with is approximately an advection equation, u tilde t plus u0, and this should be u tilde x here. The perturbation u tilde satisfies a scalar advection equation, with the advection velocity being the value of u that we're linearizing around. And as long as u doesn't vary very much from that, then this would give a reasonable representation. And so the advection equation, we know the solution simply translates without changing shape at all. If there's some small variation in u, then in reality it should deform slightly, but only slightly maybe over the time that we're looking at here. So this linearized equation would be a very good model for what's happening with the nonlinear equation. So that's the idea of linearizing a nonlinear equation, getting a simpler linear equation that's valid in the special case of small perturbations around some state. So now let's look at compressible gas dynamics. So compressible gas dynamics models a gas that can be compressing and expanding as it's moving down a one-dimensional pipe, in this one-dimensional case. And so we looked at these equations before. We have the density rho of xt can now vary with space. And we also have a velocity u, but what comes into the conservation equations is the momentum rho times u. And we end up with equations for conservation of mass, or as we saw previously, the flux is just rho times u, which is the mass density times the velocity it's advecting with as it passes by a point. But then rho u is also the momentum, and it has a flux which is rho u times u, because it's also being carried along at speed u. Plus there's this additional term that comes into the momentum flux, which is the pressure. And so we get these equations, and they're nonlinear now because these functions are all functions of x and t, and we have products of them coming into the conservation law. And remember that we also have some equation of state that relates this pressure that comes into the momentum equation to the density. And later we'll look at more complicated situations where we also have the pressure depending on the temperature, for example, and then you also need a conservation of energy equation. But these equations are sufficient for modeling certain situations. And in particular, if we have, say, a tube of gas where the density is almost constant, and say the velocity is 0, or the bulk velocity is 0, it's not moving, it's just almost constant density, but there's some small perturbations, then those small perturbations are going to propagate according to this nonlinear system of equations. But if the perturbations are very small, then we can linearize the equations and get a good idea of how those perturbations will travel in the pipe. And what we'll end up with is the acoustics equations. If you have small variations in pressure in a gas, those are exactly sound waves. So to linearize, we'll assume that the density is nearly constant and the velocity is also nearly constant, could be 0. Or we'll also look at a more general constant flow at some steady velocity with linearization about that. And so then we're going to look at a case where the solution rho and the momentum rho u are functions of x and t, but they're roughly equal to these constant values, rho 0 and rho 0 times u0, plus some perturbations. And here I'm writing the perturbations as perturbations in rho and perturbation in rho u. So I'll put the tilde over rho u to indicate that it's a perturbation of the momentum itself. And we're assuming now then that our state q is some steady constant state plus small perturbations as before. And so going through exactly the same steps we had before, we can linearize this by a linear system of equations where A is the Jacobian matrix for this flux function. So what's the Jacobian matrix in this case? Well, here I wrote out the equations again, and it's important here to note that when we compute the Jacobian matrix, we should think of the two conserved quantities, Q1 and Q2, as the quantities that we're differentiating with respect to in defining the Jacobian matrix. And so the flux function, F, should also be written in terms of the Q variables. So since Q1 is rho and Q2 is rho U, the first component of the flux, this rho U, is just Q2, the second component of Q. And the second component of the flux, well, we have a rho U squared, which we have to write in terms of rho U and rho. And so that's the square of rho U divided by rho. And here the notation gets a little messy, unfortunately, but the Q super 2 represents the second component of Q, but then the other 2 in the exponent there is a square. So apologize for that. I've struggled with how to choose notation that would avoid this problem, but we'll be using subscripts so often for other things as we go along that I decided it's best to just use superscripts for the components of Q and be aware that sometimes a superscript is a square. So we have this is rho U squared divided by rho, which gives us the rho U squared term in the flux. And then we have P1 of rho, which is P1, some function of Q1. And now to calculate the Jacobian, we have to take this flux function where things are represented as F1 of Q and F2 of Q and differentiate F1 with respect to Q1, F1 with respect to Q2, and so on to get the components of the Jacobian matrix. And so when we do that, when we differentiate Q2 with respect to Q1, we just get a 0. And when we differentiate Q2 with respect to Q2, we get the 1. And then from the second equation, when we differentiate this term, Q2 squared over Q1, with respect to Q1, we'll get minus Q1 squared over Q2 squared. And minus Q2 squared over Q1 squared, rather. So that's rho U quantity squared divided by rho squared, so that just gives us a U squared. And then we also differentiate P with respect to Q1, and that gives us the P prime as a function of, well, here I wrote it as rho 0, which is the first component. Similarly, I simplified Q2 over Q1 to be just U. And then finally, we have the derivative of F2 with respect to Q2, and there we're differentiating this term with respect to Q2, and that pulls down the 2 from the exponent, and we get 2 times Q2 over Q1, which is just the 2U0 term. A bit messy. Let's get rid of that. Yeah, so this is our Jacobian matrix evaluated at some state Q0, and again, I've written it in terms of U0 and rho 0, but those are were rewritten from the components of Q. So that's just the Jacobian matrix for the linearized gas dynamics equations. And if we write that out as a linear system, this linear system for Q tilde, linear hyperbolic system, it looks like a bit of a mess. And again, the tilde variables are the perturbations in density and the perturbation in momentum. Now, it turns out you can simplify these equations, and there are various ways to do this. It's a bit of a mess to start from this form, but if you play around with it, you can find that instead of writing things in terms of perturbations of rho and rho U, we can instead write things in terms of perturbations of P and U. And that gives finally the acoustics equations. That perturbation of P satisfies one equation, perturbation in U satisfies the second equation. And here I've introduced this quantity K, which is rho 0 times P prime of rho 0, which is called the bulk modulus of the material. It's sort of a measure of how compressible the gas is, how much it compresses when you press on it, and it's related to the derivative of this function P prime, this function P of rho, which is the equation of state that tells how the pressure varies with density. But in the linearized case, rather than needing this whole function, nonlinear function P of rho, all we care about is right around the state that we're linearizing around, what is rho 0 times P prime of rho 0, and that's just some constant K0. And this gives us the equations of linear acoustics. So here they are written again, or written as a system, and here I've dropped the tildes. Now that we've sort of done the linearization, I'll look at P and U as being the pressure perturbation and the velocity perturbation in the acoustics equations. But it's important to remember that these are perturbations around the constant state, some constant pressure and some constant velocity that we're linearizing about. And to see if this is a hyperbolic system, we need to calculate the eigenvalues of this matrix A, which is easy to do. And you find that the eigenvalues are U0 plus or minus C0, where C0 turns out when you take compute the determinant of A minus lambda I, you get a square root of K0 divided by rho 0 coming in. That's our value C0, which is the linearized sound speed. That's the speed at which these waves are propagating in the linearized acoustics equations. And often, again, we might be looking at sort of acoustic waves moving through still air. So think of a tube of gas with U, the bulk velocity, essentially equal to 0, except for very small perturbations as a sound wave travels up or down the pipe. And in that case, the two eigenvalues are minus C0 and plus C0, and that says that we have waves that can propagate either to the right or to the left through a gas, and in either direction they're propagating at the sound speed C0, the speed plus or minus C0. In the more general case, where we have a background velocity that's not 0, then that's like we have air that's flowing down a pipe, and then there's some sound that's propagating through the air, but those sound waves are going to be moving relative to the gas itself that's moving, and so they'll be moving at speed plus or minus C0 relative to the velocity U0, the bulk velocity at which the gas is moving. So those are the linearized acoustics equations, which can be derived by linearizing the gas dynamics equations. So just to summarize, if we have a system of nonlinear differential equations of this form, this first order partial differential equation, then we say it's hyperbolic at some point if, when we linearize it about some point, here I called it Q bar, I guess, instead of Q0, but if we linearize it about some state Q bar and look at the Jacobian matrix, if that's diagonalizable with real eigenvalues, then that is to say the linear system that we get by linearizing is a linear hyperbolic equation with real eigenvalues and complete set of eigenvectors. Then we call this nonlinear problem hyperbolic at this particular point, Q bar. And you can easily have systems where it's hyperbolic at some points. If you linearize about some state, it's hyperbolic. If you linearize about a different state, it's not hyperbolic. And we'll see some examples of that as we go along. But once we've chosen a particular state that we're linearizing about, and we're looking at small perturbations relative to that, then we just have a linear hyperbolic system with a constant matrix, which is the Jacobian matrix evaluated at that state. And that's either hyperbolic or it's not. And that tells us whether the original system was hyperbolic at that particular point. So we'll see various examples as we go along of situations where you get hyperbolicity provided certain conditions are satisfied. So we'll look at the shallow water equations later, where we look at the depth of a fluid H, and as long as that's positive, the shallow water equations are hyperbolic. Or nonlinear elasticity is also mentioned in the second chapter of the book. And then there's a general nonlinear stress-strain relationship, and there has to be some condition that the derivative of the stress with respect to the strain has to be positive in order for it to be hyperbolic. For gas dynamics, you end up with the condition that P prime of rho has to be positive in order for it to be hyperbolic, because it's it's the square root of p prime of rho that comes into the eigenvalues, as we just saw. And so that says that pressure has to be an increasing function of density. As you compress a gas more, the pressure increases, which is a natural physical condition. And again, you can write the nonlinear problem as a quasi-linear problem, often qt plus f prime of q, qx equals 0, which is the basis for the linearization. You can also look at this as just being the form of the nonlinear equations, but usually we don't want to use this non-conservative hyperbolic form for actually solving a nonlinear problem. We usually want to keep things in conservation form if at all possible. It makes it much easier to understand what's happening with shock waves and to make sure we're getting the right solution. And in the next lecture, I'll look at a couple of examples where we don't have these hyperbolicity conditions satisfied and sort of see what goes wrong in those cases.